Hello, ladies and gentlemen. In this presentation, I will talk about my latest research on the black basket analytic for mid-curves and spread options. As introduction, I have mentioned that mid-curves and spread options are still popular semi-vanillas. Their pricing is closely related with so-called Copularization of two fixed marginal distributions. Here we have two standard interest rates, R1 and R2, calibrated to the market, to the option markets. The main question now is how to construct the joint distribution such that the obtained spread option price, this one, R1 minus R2 minus strike, for a different set of strikes will satisfy market information. So we have not only one strike, but several of them, maybe even 5 or 7. A lot of literature was devoted to various copulas between the distributions. You can see, for example, the book of Anderson and Peterberg for a detailed review. We can mention the copula drawbacks. So let's start with that. So a standard copula has very limited number of parameters. So first example is the Gaussian copula. It has only one parameter, a correlation. If it is fixed to one strike, for example, it is not sufficient to cover the other strikes which are available on the market. So only one strike can be fixed here. We can make an alternative, a simple alternative, which is called power Gaussian copula. Again, you can see it in Anderson-Peterberg book. So it formally gives us two extra parameters, these powers. However, in reality, they do not permit to have the full three-dimensional manipulations of the spread options. Actually, low powers make the effective correlations much weaker. If they're zero, if these powers are zero, the effective correlation will be just zero between the rates. As the second drawback, I can mention numerical realization. So, it can be painful. Numerical integration can be slow, especially for the calibration of quite numerous spread options. Numerical calculations of Greeks can be slow and noisy. When we can change a little bit of integration grid, we can introduce an extra noise. And also extrapolations assumptions can give a sizable influence to the mid-curve spread option prices in Greek. So depending how we extrapolate our curve, we can have different answers. As alternative, we can propose the following. So we can say, okay, we can identify the rates with the parts of some multidimensional process. So again, example from Anderson-Peterberg, rates are driven with the Hessian processes, with some stochastic volatilities calibrated to standard option markets. The joint distribution of freedom can be associated with the cross correlations between two rates and their stochastic volatility. So the major problem here is that for the spread option, that spread option price is not available analytically. Of course, we can do this two-dimensional Fourier inversion, but it will be related with the two-dimensional complex integral. It will be even more complicated than simple, not maybe that simple, but Monte Carlo integration. So here we'll take this way of multidimensional process, but we will do it in a slightly different way. So actually we apply this idea to the basket of log-normal processes. So we have the following attractive features. So it is pretty flexible to be calibrated to standard option market. It has the same form in different measures. It has a large cross correlation of freedom to be calibrated to several spread option strikes, and it is analytically solvable. So we refer to such a basket as a black basket due to the black or log-normal processes participating inside. So just to mention several references. So first, a spread option between two log-normal processes and its approximation was introduced in Shinko more than 20 years ago. Then Carmon and Dullerman were the first to come up with an accurate option lower bound of arbitrary size of black basket by numerical optimization of its exercise boundary. And later Pellegrini gave, for example, analytical solution, which is less accurate than Carmon and Dullerman. So let's mention our contribution to this research. So the first one is the construction of joint distribution of two rates, R1, R2, both represented as black basket with several terms. Cross correlation between these two log normal components, R1 and R2, gives sufficient degree of freedom to calibrate their spread option to multiple strikes. So the second is efficient optimization algorithm of the underlying option exercise boundary. So we're free of multidimensional linear solver. So we have done a couple of tricks how to calculate the option price very rapidly. And we also did some intuition using the small time analytical approximation in the case of two element baskets. So each basket has two log normal distributions. So this can serve as understanding smile parameters when we do the calibration to individual rates. So we can see who is who and who participates, for example, which kind of parameter combination participates in the money volatility, which one participates in skew and smile, and so on. And we did quite a rich numerical experiments to have the confirmation that the good calibration capabilities, as well as parameters and hedging stability. So we will show in the very end how recalibrating our model actually leaves the parameters very, very stable. So all the technical details can be found in the supporting paper and SSRN. Setup and notations. So we denote a general forward swap, its rate and annuity as follows. So S will be our swap, which goes from T1 up to T2 and observe at little time T. So it's usual formula is just we have a difference of two zero bonds, starting from the end and from the till the very beginning, minus strike times annuity. So annuity rate will be just a linear combination of the zero bonds with the corresponding time differences, and the rate will be difference of two zero bonds divided by the annuity. So very standard notations. We have some payments dates T1, T2, and so on, which lie between the start and the end, and delta T is the difference between them. So we adopt the following notations for swap rates, and annuity with the fixing date T0. So imagine we have a fixing date T0 here and different end date Ti. So we'll just simply denote the swap rate and annuity with a subscript I. So S of I of T will be swap here, for example, observed at little t, running from T0 initial start date and Ti. Mid-curve. So mid-curve swaption is an option to enter to a swap which starts at T1 and ends at T0, and exercise date lies before T1. So T0 is less than T1 and T1 is less than T2. The difference with the standard swaption is that T0 is not the same as T1, so it starts slightly later. So the price of this mid-curve, well, in some model measure associated with some numeraire n, is the whole swap, the positive of the swap divided by the numeraire. So here we denote MC as mid-curve, right? So this MC, this value means that mid-curve. So we can also introduce mid-curve objects with this subscript MC. So SMC is our swap rate from T1 to T2. We can rewrite, of course, this pricing formula in the annuity measures associated with the with this mid-curve annuity, this one. in a very simple form, under which the mid-curve forward trade process is martingale. So easy. Now we do the same thing with the spread option. So the spread option gives the right to exercise at date t0 to pay a spread between two rates versus a strike. So we have R2 minus R1, which I measure t0 minus strike. So naturally, the spread option price in a TP forward measure, TP is a payment date, will be expectation of this payoff R2 minus R1 minus K plus, because the numerator, this T0 will be simply 1. So it's trivial, and let's do not waste time on these definitions. Less trivial subject is a rates interpolation. We can say that in both mid-curve and the spread option, we have different rates which are linked together, and they're non-natural measures. So the measures which we link them in these options is not martingale measure. As far as we work without the term structure models, but only relying on the market information, we need to express different trades or other annuities and swaps and so on through other rates, for example, the CMS rates. So this can be achieved by yield curve interpolation. So imagine we know how we move two parts of the curve. So using some interpolation, we can say that how, for example, the middle of this curve will move, how all the possible zero bonds will move. So we'll omit the further details, but we just state that the rates distribution, the non-natural measures, of course, can be expressed via the rates in the natural measure, and we pick up the simplest linear representation here. Black basket rate representations. The black basket form is a rate representation as a sum of log normal black processes. So such that the rate in the martingale measure can be represented as the sum with some center, and the weighted sum with certain weights alpha I of log normal distribution. So I have exponential of sigma I, which is a natural volatility. We have a wi, which is the associated Brownian motion, minus, of course, this part to make them martingale, minus 1. So the average, of course, of this participant will be 0. So sigma I, as I said, the volatilities, we have weights alpha, and correlation ij between different Brownian motion, wi and wj. Couple of interesting remarks. So the black basket is a generalization of the displaced diffusion process, and now it have enough degrees of freedom to be calibrated to a smile. We can have 2, 3, and so on, as many exponents as we want. So can we make it very flexible? The second remark is that for the single rate distribution, we can use 100% correlated Brownian motion. So we can put all these W's the same. But for the main black basket usage, multi-curves or spreads, Brownian motion decorrelation, such that the correlation between the Brownian motions is not equal to 1, brings an extra degrees of freedom. For example, if two of them, if two rates are decorrelated between each other, the mutual correlation of freedom is the biggest. Some features of the black basket. So the first, of course, the black basket option can be solved analytically, so we can check it in my paper. Importantly, product of two black baskets and their linear combinations can also represent in black basket form, so it's sort of algebra. So this means that the rates in different measures still keep the black basket structure. We don't need to do some tweaks around to bring it up. Approximate demand volatility of a black basket can be very easily calculated, just sufficient to expand this black basket exponents for small times. So we just say that we have our center plus the approximate Gaussian form, which is this weighted normal distribution. So of course the money distribution here the money volatility here is simply it's square weighted with the weights alpha and alpha j and the correlation. So very easy. So approximate skew and curvature can be obtained for some special cases, including a case of two exponents. Actually, the case of two exponents will be our main working horse, but of course we can do a structure with a more rich, more with more flexibility. So anyway, consider a case of two exponents. Very first generalization of the space diffusion with the opposite vol. So the volatilities will be here sigma, and here's minus sigma. So this is the case where we have the most flexible skews and smiles. So this, as I said, biggest smile effect is when alpha I is equals to minus alpha 2. Alpha 1 is equals to minus alpha 2. So, and we have sort of hyperbolic sine form. So this is quite cute guy, and so you can calculate different characteristics of this distribution. You can check it in the supporting paper. Our working horse will be general two exponential form. So we have sum of two exponents with different Brownian motions, somehow correlated or decorrelated. So we have sigma 1, sigma 2. And alpha 1 and alpha 2. So actually this decorrelation between Brownian motions, so they can be, for example, in our examples, will be correlated to 0. So this decorrelation gives us an extra freedom and calibration to mid-curve and spread options. Let's give some intuition of the black basket option pricing, how we approximate with the high accuracy the black basket option price. So we have our O, which is option price, which is expectation of the weighted sum of the Gaussian exponents. So we have AN some constants. ZN it is a zero mean normal with certain variance, VMN here, and so it has its. Actually, we can put the strikes inside, for example, with zero variance. With a zero variance, well, zero variable Zn here. So that's our guide to calculate. And so let's say that the exercise boundary B of this option as a function of all the factors, of course, nonlinear function of all the factors Z's of these Gaussians, such that it's equivalent to the fact that this sum is more than 0. So it's just our definition. So B more than 0 means that we have that. Of course, we can approximate this boundary by a linear function of the Gaussians. Like this, B will be approximately equal to some linear combination of our Z's weighted with the numbers beta minus B, which is supposed to be the kind of linear boundary here. What can we say about this approximation is that the error here, the approximation error here, is very accurate. So its error is strongly attenuated with a small underlying. We have this our sum in the vicinity of the exact boundary. So nearby the exact boundary, we can have some, our real boundary can be a little bit out of this exact boundary. However, the underlying here is very, very small. So that is why the whole error is tiny. So once the boundary parameters B and beta are fixed, we can explicitly calculate the option price approximation like this, using the Gaussian cumulative distribution function. So this is a simple exercise and very fast. You can see, of course, the details in the paper. The most accurate boundary approximation is attained when, of course, we find B star and beta stars, which maximize the approximate price. So we have we can look for B and beta such that this Gaussian approximation actually give us the maximum of the price. So this O star will be our price. And this optimization was proposed by Carmona Durelman using a nonlinear solver with, of course, all its potential drawbacks like slowness and the noise. In my paper, we have suggested a simple explicit iterative procedure which, performs in like 5-10 iterations. And of course, it's more stable. So let's give some graphs on the rate calibration, how it works. Let us start with examples of the rate calibration to European swaptions. Just we fixed one rate and we forgot about everything and try to see how it can be calibrated to the real life smiles. So we take European swaptions in euros and the observation days of the 3rd of April. The black basket form appears to be flexible to fit the market smile. We'll see it on the next slides. The calibration uses a numerical solver with an initial guess provided by analytical approximation. So again, several iterations. And in the plots below, we'll find the calibration accuracy of several swaptions with 1 year expiry with a relatively pronounced smile. So we can see that, for example, European swaption 1 to 5 years, we see that the orange is calibrated black basket and the target option is blue. So we have only little errors here when the option goes for the extrapolation. Here for this 10 to 10, so very, very accurate calibration. We can represent a mid-curve or a spread option, both of them, of course, as a generalized spread option, such that we have weighted sum of rates R1 and R2, little one R1 and little R2, weighted with some coefficients, delta 1 and delta 2, and of course some strike. We put here the zero means for both rates. We have alpha 1 and this whole sum for the first rate, and for the second rate we'll have subscribe 2 here. So this is the first rate, this is the second rate. The rate parameters in the unnatural measures can be calibrated using the following information: the rate's natural distribution, of course, and the rate interpolation. So we suppose we have already calibrated both rates, and all these parameters are fixed for their own standard option markets. Now the cross correlation. Now how can we modify the joint distribution plane with the cross correlations? So the cross correlation between two vector Brownian motions W1 and W2, both of them corresponding to the rate 1 and rate 2, is actually defined like this. So I have Cij and determines the calibration of freedom for the general spread option. So we have general spread option. We have this rate with the Wi here and W1 here, and the second rate with the W2 here. So all the parameters are fixed except this cross correlation between W1 and W2. If this Brownian motion were fully correlated, so such that W1 will be just for all the i's will be equal to W1, the spread will be driven by only one number, the correlation between W1 and W2, because they are correlated to one number. And this, which is equivalent to Gaussian Copula. So without going into details, we can say that we can actually parameterize the cross correlations with angles theta I and theta j, which corresponds to so-called given rotations. And so having this correlation freedom, we can come up with a very rich cross correlation structure and very rich calibration capabilities to the spread options with multiple strikes. The final part of the presentation is devoted, of course, to numerical examples. We'll consider challenging experiments in the calibration of spread options to multiple strikes, and where we, of course, need a lot of degrees of freedom of the decorrelation and, of course, more rich copulas. For this, we decorrelate to maximum our internal Brownian motions. So internal Brownian motions for each rate will be correlated to 0. In our experiments, we'll concentrate on 10 years spread between 10 years option and 2 years option with a 1 year of maturity. We will work with a compact case of 2 exponents, and because we have 3 different copularization parameters, 3 different handles to organize the structure of the option, and will lead to very small calibration errors. So you can see that this gray line, this is our calibrated results, and the blue line, this is the target. This is the observed option prices, observed option normal implied volatility. So you see that the calibration errors are very small. This slide actually shows how can we manipulate with different parameters while the volatility is pinned. So because we can check in the paper, but here we show that the main handle, main angle, theta 1,1 is controlled for at the money level for the spread option prices, while the other angles in this given rotations parameterization can put them up and down. So you see, this is quite flexible structure, so we can indeed play with the whole spread option smile using these angles. Couple of comments on clarifying and observing these experiments. We have used a 2 exponential black basket setup. Obviously, a high number of exponents gives a larger calibration of freedom and the wings control. The speed is very important here, and the calibration to multi-strike option. So as I said, we have developed an acceleration of the Carmona-Durman procedure. The internal correlation inside each rate is the tuning parameters, and we chose it being 0 for the largest calibration of freedom. As I said, the biggest freedom of movements of the generalized spread option or spread option smile with the pins at the endpoint occurs when the underlying rates have a similar characteristics. So as in the spread option, for example, in the mid-curve options, this freedom is less big because factors delta 1 and delta 2 can be pretty different, and the smile is less dependent on the small correlation by its construction. Another series of experiments is stability. So, of course, an attractive property of any model is its time recalibration stability, when it keeps stable parameters after a series of recalibration. Here in our numerical experiments, we do the following. We take a unit, unit notional mid-curve swaption of 1 year up to 1 year, 5 year, 5 year, with a strike of 10 basis points. We move the observation date through 1 month period, so from the 4th of April up to 4th of May, and observe what happens with the option price and its parameters. So for running observation date T, we build 2 black basket models with maturity 9 months and 1 year. So just in between our movement, they correlated, of course, to standard European options with the enveloping maturities, and at the money mid-curve options again with the enveloping maturities. So we interpolate the model coefficients linearly in maturities to obtain the price of our option as a function of these thetas. If you remember, this is a cross correlation angles. And gamma and sigma, with the schematically denote all the calibrated standard traits and implied vols. So gamma and sigma, it's our somehow factors. They move, they're supposed to move in time, following the European option parameters. And thetas, angles, they're supposed to be the parameters, so they should keep the same. So we can analyze their dependence on the time. So, as I said, the dependence of the option price from this cross correlation angle, from cross correlation angles, is actually the main is so-called stability. So, in our plot below, we'll see how it's very mild main angle time dependent. So it changes over 1 month by 25 basis points. So it's very, very little one. So given its sensitivities to this angle around 20 basis points, the noise result, do not exceed a couple of basis points for the flat volatilities. So we see that angle keeps very, 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 very stable. That's the main angle. Right. So the second experiment is the hedging stability. So we analyze how the initially hedged portfolio, how it disintegrates in the future. So we'll see that disintegration is very, very low. So it means that the model fits well in the market. So to analyze stability of the hedging portfolio, we use the following experiment. So at the settlement date, again, 4th of April, we create a hedge portfolio of 2 underlying forward started swaps to hedge, to have the delta hedging, and 2 European options with 3 different strikes for the dagger hedging. Of course, this at inception, these portfolio sensitivities are 0 or almost 0. So we start with this hedging portfolio and just see how it goes, how it varies with the time. So we follow this portfolio for 1 month without, of course, re-hedging, just keeping the same, and compare with the naked mid-curve option. So see, that's this no hedge. Of course, it's very noisy, and this hedging portfolio is very, has very little movements. So we can say that we have a dramatic reduction in realized normal volatility from 70 basis points, which is supposed to be of the uncovered mid-curve option, to 5 basis points of the hedge one. So this experiment shows that the frequent hedging of the mid-curve is not necessary. We can keep the same hedges at least for 1 month. So to conclude this presentation, I can say that we have developed a new way to unify 2 fixed distributions such that their joint behavior has a highly parametric form, highly flexible and very comfortable, such that the corresponding option on a linear combination of the 2 distributions can be calculated analytically. We can combine, we can multiply one underlying to another, and it will still be this new black basket form. We have applied this technique to mid-curves and spread options and show clear practical advantage of the approach. Thank you very much for your attention.
Hi there, welcome back everyone. So we're now going into a Q&A session. So we've got a good few minutes left to be able to put some questions to Alexandre. So you'll all see that there's a box on the right-hand side where you can type in your questions. So without further ado, Alexandre, let me put the first question to you, which is, what are large deviation asymptotics of the black basket?
Thank you. So it's a nice question, actually. If all the Brownians inside this basket are correlated to each other, right, then the asymptotics will be log linear, so relatively fat tails. The opposite case, just hypothetically, of course, if this basket contains infinite number of assets and of infinite number of exponents, and each exponent is not correlated with each other, as we know from the central limit theorem, it will be normal asymptotics. So either log normal, quite thick, or the other limit is normal. So kind of the real ones are in between, more or less.
Great, thank you. So the next question that came in was, again, could you give more details about the power Gaussian copula?
Right. So actually, we can represent power Gaussian copula in terms of the credit the loading factor loadings, in some sense. So actually, let's take our uniform, which corresponds to the Gaussian copula. So, and then we say, okay, this guy will be actually our real factor, and then we can add in some idiosyncratic factor, like in this factor loading. So we take a correlated Gaussian and we add another uniform which is not correlated with anyone. So we put them in certain powers to meet, for example, the right mean and so on, and we take the maximum. So the maximum of the so the new uniform of the this Gaussian of this power Gaussian Copula will be maximum between the old uniform in certain power and the idiosyncratic uniform in certain power. So in this sense, if we, for example, set the power to 1, we will get exactly the Gaussian Copula. If we set the powers to 0, the resulting uniform will be simply equal to the idiosyncratic factors. So we'll kill the correlation completely. So this model actually effectively decreased the correlations. So that is why I was saying in the presentation that it is not maybe the whole, we don't have the whole freedom, whole three-factor freedom for this model, because it effectively decrease the whole correlation. That is why it is not maybe so widely used among practitioners.
Mm-hmm. Great, thank you very much. One more question in here. So we've got, can we use the black basket as a term structure model?
Yes, actually we can, because we have its integrability doesn't depend on the intermediate characteristic of the process, but it can be done. You know, the system is always integrable for whatever time-dependent operations we have. Also, as I mentioned, this black basket process is a generalization of the displaced diffusion, right? And we know, for example, we can use the displaced diffusion model in the LMM. For example, you know, it's like one of the most popular. In such sense, we can easily replace it by the black basket by, for example, 2-exponent black basket or with one constant, which introduce in this LMM, you know, the natural smile without without going to the stochastic volatilities. Moreover, and this model will be still exactly solvable. We can calculate the options and so on using the technique which I've proposed.
Great. So I'm just pasting a question into the chat there because it's quite a long one. It might be easier to read it. Would there be any additional challenge if the option underlines are very long? For example, from 13 years to 2 years, CMS spread option with maturity. I presume that's 30 years. Yeah.
Of course, it can be potentially a challenge. However, this approximation is still very accurate if we go very far. Actually, it doesn't really matter. The asset should not have too big decorrelations or too big intercorrelations. And the good news in general in our market is that for far options, the volatility is almost normal. So we have normal smile like this. So it's not, we don't have, so it's very, very normal. So to link to normal distributions, pretty easy. However, in this case, we will lose a little bit of this decorrelation freedom. You know, we can decorrelate in whatever means to normal distribution. It will still be normal. So here there is almost, you know, no control. But yes, you know, formally we can use it for quite far maturities.
Great, thank you. So the next question is, the formula that you exposed applies, or does the formulas that you exposed applies only in a single curve framework?
Well, as I said, this framework is quite flexible. We can take one black basket, we can multiply it by another one, so it's still a black basket. So it's sort of mathematically speaking, kind of algebra. So if we represent our FX rate in a certain combination of exponents, of course, we should be careful that it's always positive. then product of FX rate and our interest rate, will also be black basket. So we can also calculate its option pricing and so on without any problems.
Great. So next question. Does the black market method have any value in modeling a single factor?
Well, so of course we model in a single factor. We model these options. We model them using the Saber or some variations of the Saber. So that traders feel quite well the Saber parameters. Here, this is maybe something artificial. However, as I said, as a term structure model, people use shifted LMM, which is simple with respect to I don't know, our smile, which is rich. So maybe in one factor model, the usage of this black basket stuff is more like term structure, generalization of, say, LMM.
Great, thank you. So, ladies and gentlemen, we still have a minute or two left. So if you do have any questions, please submit them now. Of course, you will have the opportunity to connect with Alexandre after the session, and particularly if you're watching this session on demand. Of course, Alexandre won't be here live to answer your questions, but you can click on the link at the top of the page, the attendees list, and you can find Alexandre's name and you can send him a message via the platform. And he'll be able to pick that up in the next week whilst the platform's open. I can see that we may well have answered all of the questions. So I think we will then wrap up the session. Thank you so much for joining us, Alexandre.
Okay, thank you very much for your attention. It was a pleasure and privilege, and see you next time.
Yes, we'll hopefully see you face to face next time round. Thanks very much. Take care.
Bye-bye.